Good evening and welcome to Everything Matters, Tales from the Periodic Table. Tonight, Vanadium. How many people have heard of Vanadium? Oh, a few people. Wow, that's really cool. So I hope that you all received your collectible card. You all have your collectible card. They're collectible. And if you have been here, you have 22 other cards too, starting at hydrogen. Tonight we're on the 23rd episode of, that means that's a season. Wow. We have a whole season of Everything Matters, Tales from the Periodic Table. And we do have some, if you don't have all of your cards, I think we have some substitutes, some older ones on the back tables there that you can fill in your collection with. I think you should come to all of them and get them at the time, but there we go. Who's been to After Dark before? Our Thursday night events here. Just want to take a quick survey. Not many of you. Wow. How many people here have been to Everything Matters, Tales from the Periodic Table? It's our longest titled talk. Good. Well, we hope that you all enjoy tonight. We're going to divide this talk into two parts. So when I'm done, don't get up to leave. There's more. Wait, there's more. I do the marketing thing. Speaking of marketing, we actually have calendars. It's a little late in the year, I know, for calendars, but if you go to our store, we do have Everything Matters calendars in 2 different sizes. I just wanted to mention that. Oh, and my favorite book, by the way, if you're going to get a book about elements, my favorite book by Theodore Gray called Elements. Awesome book. You'll see some of his delicious artwork here tonight. I'm going to be followed by Sarah Cohen, and I will introduce her. She's going to talk about the really interesting chemistry that goes on, some of it involving vanadium in tunicates or sea squirts. So that's going to be after I finish talking, so don't go away when I'm done. So let's begin. Vanadium. Here's our periodic table. Everybody's familiar with our periodic table. We've all seen it all of our lives. This is one from the Elements, from Theodore Gray's application, which you can get on your iPad. I'm really marketing for him, aren't I? It's an awesome book and an awesome app. And vanadium is over here. It's element number 23. So we have, last month we had element 22, titanium, and coming up in September, because we're going to take a little summer break, we're going to do chromium, so that's the next element, 24. Vanadium, as I mentioned, element 23 is, its atomic number. That number 23 tells you how many protons there are in the nucleus. There are variable numbers of neutrons in the nucleus, but there's always 23. If it's 23, it's vanadium. And we'll talk a little bit about the variable number of neutrons in the nucleus a little bit later. Now, vanadium it's been around for a while. Well, it's been around since forever, but it was discovered in 1803 by this fellow who is a very famous Mexican chemist, Andrés Manuel del Río. Famous enough that he has his own stamp. And I notice that the date on the stamp there is 1764 to 1964. I don't think that's when he died. No, that would have been 200 years. But he actually discovered this in samples of ore. He didn't actually refine the metal, but he discovered the fact that there was an element, something new in these minerals that he was given. And that was in 1803. There were other chemists at the time who looked at his work and said, no, we don't think so. You probably got it wrong there. He thought it was a new element because he found these compounds of some new thing he thought was new, and they were really colorful. They formed compounds of all colors. As a matter of fact, he called the element that he thought he had discovered panchromium, from the Greek panchromium, meaning all colors. And then he thought, no, that's not a good thing. They're mostly red compounds, so instead I'm going to call it erythronium, from the from meaning red. Your red blood cells have that same root in it as well. But then his colleagues said, no, you just rediscovered something, compounds of chromium. So he withdrew his paper. And he originally did not get credit for discovering vanadium. And some of the minerals that he was looking at, and these are just the most gorgeous minerals. Here's one that is now called vanadinite. And look at that beautiful red color. It's just gorgeous. It also occurs in a different mineral, beryl. And notice that you don't see vanadium in the chemical formula here. We actually used this for beryllium when we did beryllium a few months back. But beryl, if it doesn't have any impurities in it, is absolutely clear. But impurities in beryl cause it to be green, or we also call them emeralds. And one of the colorants in beryl to make it green is chromium, which we'll talk about in September. But also, vanadium is another colorant that causes it to turn green. So beryl or emeralds are, some of the coloration is due to vanadium. Here's another beautiful shot. Here you can see a beryl crystal in I think it's a calcite matrix there. Just beautiful thing that we had on display when we did beryllium. Another cool, look at the colors of these minerals from vanadium. Cavensite, just a beautiful mineral. Hydrous calcium vanadium phyllosilicate. I had to read that one. And one final mineral that is actually pretty interesting that they get vanadium from is this one called Karnatight. And you can see here there's the vanadium is in there. Vanadium has the letter V, but notice there's also some U in there as well. I actually have a piece of Karnatight here, and I'm going to put some gloves on to handle it. I just don't want to get it on my hands because of the U that's in there. Anyone know what U stands for? Which element U is? Uranium, right. So this is a sample of Karnatight. I'll just show it to you here. It's just a beautiful, it's kind of crumbly mineral. I'll show it to the camera here. Maybe we can, I don't know if we can put that camera up on the screen. Can we do that? No, it's okay. Well, we have a good picture of it on the screen. The folks at home on YouTube get to see the nice close-up of the Karnatight. But the U in here stands for uranium. And if I turn on a Geiger counter here, you will notice that, let me turn up the volume so you can hear it. Actually, even way out here, it's seeing it. So this is actually mined for uranium, mainly. There we go. It's mined for uranium, but it contains quite a bit of vanadium as well. So this is another source of vanadium. And I will just leave that there. It's giving off gamma rays, actually, so you can actually hear it even through the can. Yeah, don't worry. You're fine. Trust me. This has been in my garage for like 20 years now, so I think I'm still normal. I used to have hair, but, you know, oh well. Karnatight. This is mined, by the way, that most of the vanadium is mined in South Africa, northwestern China, and eastern Russia, and that accounts for like 97% of the vanadium that is mined. It does occur all over the world, but those are the places where it's mostly concentrated. So, Manuel del Río discovered it, but then was told it wasn't. But then this guy came along, Nils Gabriel Serfström, and he kind of rediscovered the compounds of vanadium. He was a student of a very famous chemist, Berzelius, and he was studying the brittleness of steel and then rediscovered this compound, vanadium. He didn't actually see the metal of vanadium, though, but he did give it the name vanadium. First, he chose vanadium because of the V. He wanted an element that only had one letter in it. And he named it vanadium after Vanadis, the Norse god of beauty and fertility. So that became vanadium. The Norse have a lot of female gods of beauty and fertility, it turns out. But the one that got it, there they all are, the one that got it was Vanadis. So that's where we got vanadium. So he did not actually ever see the metal. The metal actually was refined by this guy, Henry Enfield Roscoe, a British chemist. And he's the first one to isolate the pure metal, and he did that in 1867. So pure vanadium was not actually refined until 1867. And here's what vanadium metal looks like. Now I have a better piece right here, which was supplied to me by my friend Ethan, who's out in the audience there somewhere. And I'm going to put on another glove here to handle that. Not because it's toxic, because I don't want to get my fingers all over it and oxidize it. If I can get my fingers in the right holes there. There we go. There we go. Okay. Having trouble with the gloves tonight. There we go. So this, and you can come on up after. I'm going to put it back in the bag, but you are welcome to come up and handle it inside the bag. This is a piece of vanadium. There we go. And it's a beautiful, sparkly, you can almost see kind of a greenish cast from the oxide on the surface here. We'll show it to the camera so our YouTube folks can see it. It's a beautiful, shiny piece of metal. It's very, very hard. I'll talk about that in just a moment. We'll kind of keep it away from water by keeping it in the envelope here. So come on up and check that out later. Oh, we had it on the okay, never mind. Had it for a moment. You want me to take it out of the bag and show it to you? Oh, okay, good. So vanadium is, if you look at its abundance in the universe, is not the most abundant thing. It's not totally rare either. It's the 22nd most abundant element in the universe. It only makes up like a 10,000% of the universe, but that still gives you an element that's about right here in the abundance table. If we move in a little bit and look at the sun, it's not going to be much different because vanadium is actually it's about the 26th most common element in the sun. The sun is made out of elements from the rest of the universe, so you wouldn't expect it to be very different. Meteorites it's about the 23rd most abundant in meteorites. It's about the 18th most abundant in the crust of the Earth, though. So it's actually a fair amount in the crust of the Earth. And in the oceans, it's about the 21st most abundant element, making up only about, well, less than a millionth of like a 10 millionth of a percent of seawater. It's very, very rare in seawater. And if you look at it in us, it actually occurs in us. We actually have, it's the 36th most abundant thing in the human body, but it's probably one of the most rare elements in the human body. It's way down here at the end here, and its function in the human body is unclear. I know there are some people who take it as a supplement. There are some, but it also can be toxic. So is it good or is it bad? Research still has to be done. I mentioned that it was made in big stars. Well, it's actually made in supernova. So there's vanadium, and it's made in exploding, huge, massive stars. It's then spread out into the universe and then gets taken up by other stars. So it can only be made in massive stars. Our sun is not making any vanadium. So we talked about the variable number of neutrons in the nucleus. So there's 23 protons in the nucleus. The numbers you see up here, the 40 through 65 here, that's the total number of neutrons plus protons in the nucleus. So you add the number of neutrons plus protons and you get that number. It's isotope. So you can see there's isotopes. An isotope meaning same place. It's the same place in the periodic table. These are all vanadium. They all have 23 protons, but they have a variable number of neutrons. There's only one stable isotope that is not radioactive of vanadium, and that isotope is vanadium-51. Now, I say the only stable isotope, everything else is radioactive. Let's take a look at that. By the way, this makes up 99.75% of all the natural vanadium. But if it's the only stable isotope, why is it only 99%? Shouldn't it be 100%? No, but there's one more isotope that's very long-lived, and we'll take a look at that in just a moment here. So all the others are radioactive. We have vanadium-47. These are kind of the longer ones here. Vanadium-47 has a half-life. If I had a chunk of vanadium-47, half of it would be gone in 32 minutes. If I had a chunk of vanadium-48, half of it would be gone in 15 days. If I had a chunk of vanadium-49, half of it would be gone in 330 days. And the last one, vanadium-50, half of it will be gone in 150 quadrillion years. It's a really long half-life. In other words, it's not very radioactive. But it is not stable. As a matter of fact, 150 quadrillion years is actually about 10 million times the age of the universe. So there's basically as much vanadium-50 around now as there was ever. It's going to take a long time for that stuff to decay. Really, I don't even know how they measure that, actually. That is so long. You have to collect an awful lot of vanadium-50 to measure that kind of thing. So vanadium, if we look at some of its physical qualities, the density of vanadium is about 6 grams per cubic centimeter, which is in the neighborhood, a little less than iron, a little more than aluminum. Water is 1 gram per cubic centimeter. And here I've listed a few things down there. So you can see that iron is 7.8 grams per cubic centimeter and aluminum is 2.7. So it's kind of midway between the two. It's fairly hefty. So when you come up here and lift it, you can check out how heavy it is. By the way, I have, if you're interested in density, down in front of me here, there are 1, 2, 3, 4, 5, 6, 7, 8, 9 different samples. They're not all elements, because I have wood, maple, and I have plastic, PL, down there. So you just get an idea of density. They're all about the same size, except for the last one there. So you can see what density is, how much mass there is in a given volume. So very massive. Well, let's look at the table. Let's look at this graph. Here are the ones that you can see on the table. Tungsten, lead, copper, iron, aluminum, magnesium, and, oh, I missed one, and vanadium. So vanadium's kind of midway in there. It's not the super dense stuff like tungsten is there, but it's also a lot heavier than aluminum is. So check it out. Come up here and play with these later on. As I was reading, I found out something that's really interesting about vanadium, and I'm going to apologize for this next slide. I criticize people for doing this, actually. Fonts you can't read, because if you don't have 20/20 vision, this is way too small. But this is kind of a list of hardnesses of different elements, with the softest stuff up at the top here, which the top line says, see, even I can't read it, cesium and rubidium. And near the bottom, we have the really hard stuff. The blue ones are not elements. The blue ones are compounds. Only the white ones are elements. So vanadium, because I know you probably can't see where it is right there. It has a hardness on the Mohs hardness scale of about 7, about the same as quartz. So it's the same as glass. It's fairly hard stuff. And you notice that the only stuff underneath it that's harder than vanadium is tungsten, chromium, and boron. So it's like the 4th hardest element. So that's kind of distinguishing. If you wanted to buy some vanadium, depending on the purity, vanadium of 0.999 purity is about $20 a pound. So it's moderately expensive. It's not like buying iron, but it's not like buying gold either. It has a kind of a big atom compared to hydrogen. It has lots of electrons hanging out on the outside, because it has very interesting chemistry. You can identify it actually in the spectrum of the sun. Remember I said that the sun has vanadium in it because it absorbed it from those supernovas that had gone off before the sun formed. And if you look at the solar spectrum, here's the solar spectrum. Now this is a kind of this should all be in one line. So, but I couldn't fit that on a slide. So this is all stacked up. I sliced up the spectrum. Well, I didn't. Kit Peak sliced up the solar spectrum and stacked it. So there are a couple of these dark lines are all elements in the atmosphere, the outer atmosphere of the sun that are absorbing light. So there's like up here, there's two dark lines that are caused by sodium in the atmosphere of the sun. This dark line up here is hydrogen. and so on. Some of these are labeled. Vanadium, there's a couple of them down here, there, and there. There's a couple lines due to vanadium. A lot of lines in the blues. I only labeled a couple of them there, but this is how we identify elements in the sun. You take the spectrum of the sun, see which elements are absorbing the sunlight, and then you can compare that to the same kind of thing in the lab. Very powerful technique, spectroscopy. You can find out the composition of something without having to have a sample of it in your lab. We know what the sun is made out of because we can actually just look at its light. We can find out what stars and galaxies are just by looking at the spectrum. Extremely powerful tool, spectroscopy. So if you look at the actual spectrum of vanadium, there it is. It has lots of bright lines, lots. It's a very complicated spectrum, lots of lines in kind of the cyan and blue ends of the spectrum there, which is what you saw a couple of. What are the applications of vanadium? Well, there's really not many. Turns out that one of the really important ones, though, is to make steel. If you add vanadium to steel, you make the steel a lot stronger, which means that if you have a lot stronger piece of steel, you can trim it out and use a lot less of it for the same kind of job by adding vanadium. So this is a wrench that is made out, it's a chrome vanadium steel iron alloy. So most of your tools, and by the way, this is also coated with chrome, giving it that shiny appearance. We used to have bumpers on our cars that were coated with this stuff until Erin Brockovich ruined everything. No, she didn't ruin everything. Henry Ford actually had heard in 1905, actually heard of this really interesting steel in France, and he went over and investigated it, and it was a vanadium alloy of steel, and he brought it into the US and made the Model T chassis out of vanadium steel, and that means that his chassis only weighed about half as much as the competitors. So that was a real advantage. It only weighed half as much, and he only used half as much steel in manufacturing it. So the cost saving was quite substantial. So a lot of our tools that we buy, wrenches and sockets and crescent wrenches, I mean all of our screwdrivers, it's all pretty much vanadium steel. One other application, there was one application I found which is an interesting kind of battery. It's called a vanadium flow cell. They're not meant for your cell phone. As you can see, they're rather large. This is an energy storage vanadium flow cell. And here they're actually taking the vanadium chemistry and they're changing the oxidation state of the vanadium inside the battery between various oxidation states, which actually changes its color. It's really cool. This battery here will store about 1 megawatt of energy. So this might be outside of a building that has an array of solar cells, like the Exploratorium. We have 1.3 megawatts of solar cells on our roof. We generate during the day more power than we can use. We could store it in this battery, and then we could disconnect ourselves from PG&E. But as it turns out, we just feed the energy back to PG&E, and they feed it to us at night. Excuse me. By the way, the chemistry of vanadium is so colorful. I was talking about those oxidation states. You can actually look at the colors of the solutions in various oxidation states, and they're these beautiful colors, purples, greens, blues, and yellows. They're just awesome. So that's about all I want to say about vanadium, except for the fact that it does occur in our next speaker, who's going to talk about tunicates, or sea squirts, and vanadium is concentrated in sea squirts. This one's called the bluebell tunicate, and it has concentrated from seawater vanadium to millions of times its concentration in the seawater. Why it does this, I don't think is clear, but it has some amazing chemistry going on here. Here's another tunicate that concentrates vanadium. And one more thing that is not a tunicate, that lives on land, also concentrates vanadium from the soil, and that's this very unlikely looking Alice in Wonderland mushroom. It's actually not called an Alice in Wonderland mushroom. It's called amanita muscaria. And this actually concentrates it up to very high concentrations, about 500 milligrams of vanadium per kilogram. So that's half of a gram, so 1/2000th of that is vanadium after you've dried it out. The biological function of vanadium, not clear. Vanadium is in our body. We're not sure why. There may be some advantageous thing dealing with insulin processing for diabetes that vanadium supplements may help. I don't think the papers are in on that yet, but it's also toxic, so you can kill yourself with vanadium as well. So which way do you go? Again, there's a lot that still needs to be researched on vanadium. So that's all I have for vanadium. The next element that we're going to do, by the way, coming up, is chromium. Chromium is going to be on September 21st at 8 p.m. So we invite you back for that. If you want to see a sample of chromium, oh, here's a sample of chromium. Chromium is really shiny stuff. Let's see, Amaris can get us a shot of that. Our crack technical folks over there, they'll maybe can get it up on the screen there. I'll try to hold it really still. There we go. It's really shiny element. And this one you can actually handle, because this one is hardly oxidized by anything. It forms an oxide layer of its own, and then it's protected. So you can come up and handle this. This is actually pretty dense stuff, and harder even than the vanadium. Also, I do another talk, by the way, another talk called Full Spectrum Science, which is going to be not this Sunday, but next week, Thursday at 8, and Sunday at 1 and 3. And this month, just before 4th of July, we're going to be doing fireworks. So if you want to know how fireworks work, come to see Full Spectrum Science, and hope you enjoy that. And so stay there. We're going to do a quick, oh, we have a question. The question was one that I'm not going to be able to answer because I'm not smart enough, is about the Beryl and the concentrations. I don't know what the concentration is, but it's in the millions of percent kind of concentration that causes the coloration of these things. Ruby is the same way. Chromium is the colorant in ruby. So we'll get to that in September. But I'm sorry I don't know actually the answer to that question. So right now, we're going to do a quick switch over, and we're going to invite up our next speaker, and I will introduce Sarah as soon as we're there. So hang on with that. Thank you.